Have you ever wondered how your phone, rockets, fighter jets, and computer graphics know how they are positioned? Well, the answer is with this nifty thing called quaternions. So say you want to represent a rotation of a 3D object. Well, you're rotating something in 3 dimensions, right? So it makes sense to use 3 separate values, each representing a different rotation, known as Euler angles, which is shown in this gimbal here. So with Euler angles, you can get this Nerf dart to any orientation you like, through roll, pitch, and yaw control of the 3 colored axes. But in this orientation, we completely lost the degree of freedom. This is because 2 of the axes, the red and the green one, have a line, so they both perform the exact same rotation. Instead of having 3 unique ways to rotate the object, we now only have 2. This is known as gimbal lock. Gimbal lock poses a significant problem to devices that use gimbals, but also any computer program that runs on Euler angles as well. Quaternions basically say, instead of having 3 values to represent a rotation, what if we have a 4th? 3 of them that represent an axis of rotation, and 1 that represents the angle of rotation. It's like spinning a basketball on the tip of my finger, if I could do that, so I'll just use a gyroscope. This line here is the axis, and the gyroscope can rotate a certain number of degrees around it. To understand quaternions, we have to go back to rotations with complex numbers. If we graph a complex number in a 2D plane and multiply it by cosine theta plus I sine theta, we can see that it rotates the point by theta degrees. Quaternions are complex numbers, but with not 1, not 2, but 3 imaginary parts. William Rowan Hamilton, the inventor of quaternions, defined these properties that make up the basis of quaternion multiplication. So just like multiplying 2 complex numbers together, multiplying quaternions is very much similar. To perform rotations, we only have to specify an axis, an angle, and the point we want to rotate, and let quaternion multiplication take care of the rest of it. Using this formula, where Q describes the axis and angle, and P describes a point, computers can easily calculate rotations with quaternions without the risk of gimbal lock. Quaternions can also take the quickest path to a point and also easily calculate chain rotations, making them incredibly useful in our world today.